Okay, so I'm going to talk about polynomials with the Maths 1M in mind, and I actually really am going to use this particular list of things to ask yourself about for understanding a maths object. Because while polynomials are certainly functions, they actually act as objects in their own right that you can do stuff to. And one of the things about Maths 1M is that quite a lot of the Maths 1M algebra is actually about that. Because when you look at Maths 1M algebra and you go, well, there's matrices and there's vectors and there's complex numbers and there's polynomials and there's trig functions, why are they all algebra? Shouldn't some of it be calculus? Well, the reason it's algebra is because in maths, in academic maths, algebra is the general area where you look at objects and look at their properties and see if they behave like numbers do. And so you've looked at vectors and seen how they behave like numbers because you can add them and you can multiply them. And you've looked at complex numbers and you say, hey, we've got this new family of numbers, what can we do to it? How do we add them? How do we multiply them? How do we do them to powers? And we've now going to look at polynomials and say, how can I pretend that polynomial is a number? Can I do the same thing to numbers that we can do to polynomials? That's the idea behind it. So a polynomial is an expression that's got all these x's and their powers in it, basically. So an expression of the form like that. That's what a polynomial is. Okay, so when I had on my list before, what is it? That's what it is. And to a mathematician, that is all it is. It's just a thing that you write down, where those things are real numbers. Once you start doing complex numbers, you're allowed to have polynomials with complex coefficients as well. But for now, that's what a real polynomial is. The next thing on my list for understanding an object people watching on screen won't be able to see the list, but everyone in the room can hear. Next thing on my list for what is it is list of things that are and things that are not. So things that are constants are polynomials, okay, because all of these ones are just 0. E.g. 0, 1, 5, minus 17. Linear functions, 2x minus 1, 5x, that sort of thing. Quadratic. So you might have things like x squared plus 5x minus 1, x squared, who knows, minus x squared, and cubics too, etc. Whoa, no 4s in a cubic. Okay? So any number of things, it could have all 4 of the coefficients, it doesn't have to have all of them. They're things that are polynomials. And that's pretty much the idea of a polynomial. And I have neatly said, well, here's a list of the special types. The quartics are the next one, but you can figure that one out too. Okay. That's what, yeah, okay, we've done that. Know how to represent it, know ways to represent it and how to convert between them. Okay, so we could represent them like this. Okay. So we've got our ordinary form where it's all just expanded out. There's also like a fully factorized version. So you might have something like that. That's a particular way of representing it. And we need to know how to convert between them. So factorizing, we'll get to that in a second. Well, no, we'll do it now. How do you factorize stuff? Well, you have to guess it. Okay, that's going to take us a bit. So we'll get to that in a second. There's also the graph. So for example, you might have, x squared plus 5 would look like this. Okay? Now this is a really good point. We should actually have a good idea in our head of what they look like as graphs. So what we're thinking of it here is that we're actually not thinking of x squared plus 5 as just an x squared plus 5. We're thinking of it as y equals x squared plus 5. So actually thinking of it as a function where you put stuff in and you get stuff out. So technically it's a graph of a function. So we should have a good idea of what they tend to look like. Okay, so what do our constants look like? So some graphs. Constant polynomials will be like that. Okay, this would be just, y equals 5, for example. Linear will have a tendency to look like that, say, or possibly going downwards. My quadratic, you might have one that it might go up, or alternatively it could go down. Now, what tells me whether it goes up or down? I'm asking you.
Sign.
Sorry?
Minus plus.
The minus or plus. And where is that minus or plus?
Is that the coefficient of the x squared?
Coefficient of the x squared. So this is something like coefficient of the x squared is positive. That's what this one is. Coefficient of the x squared is negative. Cool. Cubics would be next. Whoa. Well, your cubic has the tendency to do that. It may not have any wiggles in the middle because it might possibly be nice and it might just be like that, for example. It does go on forever, it doesn't have asymptotes. Or possibly it could be up the other way. How do you tell if it's this or this? There's lots of whispering going on. What is it?
Positive or negative?
Positive or negative. So this one will be that the coefficient of x cubed is positive. That's what this one is. And this one is that the coefficient of x cubed is negative. Whoa. So you see that if the coefficient is positive for the cubic, it generally goes up. And if the coefficient is negative, it generally goes down. And that's the same for straight lines. Coefficient of x is positive, slope is positive, it generally goes up. Coefficient of x is negative, slope is negative, generally goes down. So the same thing is true of all possible polynomials. Let me do quartics as well. So if you've got a quartic, it will tend to have both of its ends will point in the same direction. It just might have more wiggles in the middle. Okay? It is possible for it to face the other way. And the same thing will happen. This is the coefficient of x to the 4 is positive. This is the coefficient of x to the 4 is negative. Okay? So with a quartic, how many places can it turn? See these turning points. How many could it have?
3.
3, obviously. What else could it have? Sorry, it could have a point of inflection. I'm just asking what number of turning points can it have? It can have 3. What else can it have? 1. It can't have 2 because both ends have to point in the same direction. It can't turn twice because that would mean that it would end up pointing down at the other end. So your quartic can only have an odd number of turning points. And the same deal with anything to an odd, even, the biggest power is even, it can only have an odd number of turning points. And anything the biggest power is odd, it can only have an even number of turning points. So it's just good to know those sorts of things. And the coefficient of the biggest power tells you which way up it is. Whether, basically it's actually the right-hand side. If the coefficient of the biggest power is positive, the right-hand side will be pointing upwards. And if the coefficient of the biggest power is negative, the right-hand side will be pointing downwards. Oh, I shouldn't be putting that on the bottom of the trig functions because I'm going to mix them up. Okay. So now we've found ways of connecting them to other stuff. Great. And what they look like. So we know a graph way of representing them. And we've got a small amount of information on how to convert between the graph and the polynomial. So if you were given some pictures of polynomials and you had some options for what their formulas could be, you should be able to figure out what they are just by having a quick look at which way up they are and how many turning points they have. All right, so before we move on, we should make some connections. Are polynomials part of a bigger class of things? Well, technically they're functions, so it's there's functions. Do they contain a smaller class of things? No, probably not. In some ways, are they similar to other things? Well, they're similar to all graphs in that if you shift the x's and the y's, you'll be able to turn it into some other picture somewhere else. And they're certainly different from most things in that you had talked about domains and ranges of polynomials. Well, the domain is everything. There is no places where it's undefined. An odd polynomial, like x to the odd power is the biggest power, will always have range everything, because you can go up forever in one direction and down forever in the other. Whereas an even polynomial will always have a minimum or a maximum somewhere. So it's just good to know how they relate to the other stuff that we do in Maths 1M. All right. Ooh. What can we say about it? So, what can we say about polynomials? Things to say. Okay, well, what things could we say? We could say what the degree is. That's the highest power. So for example, x to the 7 plus 5x to the 6 plus x to the 3 has degree 7. And once we know the degree, we can know that that it will have its opposite ends pointing in different directions because it's an odd degree. We know it can have at most 6 turning points, and it has to have an even number of turning points. And we know because the coefficient of the first term of the highest power term is positive, it has to go up on the right-hand side. So there's a whole lot of information just from that number, the degree. Okay? What other properties might a polynomial have? And let's just have a look at your little book of notes. Here they are. Nope. Where are they? Oh, here they are. Oh, it also has a leading coefficient. Which is the coefficient of the highest power. Now, leading is a misleading term in that that's assuming that we've written it with the highest power first, but we could have written it as, in which case the leading coefficient would be 1, okay. That's stuff we could say about it. Okay, that's pretty much all we could say about it. That's what we could say about a polynomial. Well, what about things it has? It might have zeros. It might have zeros. So your zeros, now there's three ways of talking about these. You can talk about a zero of a function, you can talk about an x-intercept of a graph, and you can talk about a root of a polynomial, I believe. That's the way that you talk about them. Now you can talk about zeros of functions too. So thinking of it as a function, C is a zero if P of C is 0. And that's thinking of my polynomial as a function. That's really badly written, sorry. Okay, now what we should know is how to find the zeros. Well, the only way to do that is to be able to factorize it. To find them, we must factorize. Okay? Alright, what else might it have? As a function, it could have a derivative of, or turning points, or inflection points. So, as a function, it has derivative, turning points, inflection points. Okay, so your turning points would happen when the derivative is 0. Your inflection points would happen when the second derivative is 0. Of course, it might not have any turning points, but in general, and it might not have any inflection points either. In general, odd degree polynomials must have an inflection point somewhere because of the way that they're shaped. And even degree polynomials must have a turning point somewhere. So because both opposite ends point in the opposite direction, in the same direction, so they must have a turning point. What else could they have? Yeah, that's about it, I reckon. Right. Cool. So, now we're up to what theorems tell you about it. So theorems there's a remainder theorem and there's the fundamental theorem of algebra. So there's the remainder theorem, which we'll have to get to in a second. But the remainder theorem basically says that if P of x is equal to x minus a times q of x plus r, then P of a is r, basically. Which has its corollary, that some people call this the factor theorem. If P of a equals 0, then x minus a is a factor of P of x. Now at the moment I'm just sort of looking through to find all the theorems, but we haven't actually made a good plan of what any of this means because we haven't defined what factor means. So back on our list of things it could have factors, which would be polynomials that divide evenly into it, but you can factorize them to look like. Okay, so I should have put that back here. No room for them. Okay, but they're the theorems. Technically, I don't know if you were told this theorem, but there is the fundamental theorem of of arithmetic, which says that any polynomial can be factorized into linear factors using the complex numbers. So, the fundamental. Any polynomial interlinear factors using complex numbers, which may or may not have come up when you did complex numbers. Oh crap, it's not algebra, it's not arithmetic, it is algebra. Because it's here in your notes. Fundamental theorem of algebra. A polynomial can be factorized into linear factors using complex numbers. Cool. Okay, so that theorem is not technically in the section on polynomials, it's in the section on complex numbers. And you'll find that in a course, especially a maths course, that if you want to find everything there is to know about something, it won't all be under the heading of polynomials in your lecture notes. It could be somewhere else, pardon me. Because of course we couldn't know the fundamental theorem of algebra without knowing more about complex numbers. Okay, what's next on my list? What can you do to it? Aha, this is the point where we start to think about them as numbers. What can we do to polynomials? You know, as numbers. So what can we do to them? Well, we can add them, because we'll just add the matching coefficients. Because that's something we could do to numbers. We could subtract them and that would be the same. That's similar to adding them. We can multiply them, which would be just expanding brackets. And we can divide them. And this bit is harder, because dividing anything is always harder. And there are two important things to know about division. Sometimes it won't come out to be a polynomial anymore. In the same way that if you divide two whole numbers, you won't necessarily get a whole number as your answer. 2 divided by 3 is 2/3. Same thing will happen to your polynomials. If you divide them, what you might get is a rational function. And they're called rational functions because of the same reason we call them rational numbers. So rational numbers are produced by dividing integers. Rational functions are produced by dividing polynomials. So and here is where we start the one process that you may never have seen before, and I'm going to do an example of it. So you can divide any polynomial by any other polynomial. It may be that you can't do anything. If the degree on the bottom is bigger than the degree on the top, pretty much stuff, that's the best you can do. If the degree on the bottom is smaller than the degree on the top, then you're onto a winner and you can convert it into polynomial plus rational function. So what this is designed to do is it converts, or it's not an R, is it? I won't do Q because that's normally what's left over. D. No, Q. Yeah. Convert that to QX plus RX on DX. That's what it does. Okay, so we can convert it like that, or if we like, PX equals QX dx plus RX. Now this is called the quotient, and this is called the remainder. And our aim is to do this in such a way that my Rx, that's brackets, has lesser degree than my dx. That's a cue here. Sorry. The longer I go, the worse my writing gets. Okay, and it's a process designed for doing that job, and what will end up happening is you'll get a polynomial and then some other rational function left over. But you might, if you're really lucky, just get this. In which case what you've managed to do is factorize p of x into two polynomials. So that's what polynomial division is for. Technically that wasn't an example. Now let's do an example. X cubed plus 5x minus 1 divided by x squared plus 1. Okay, so the way that polynomial, I'll change this to a 4 so I've got enough work to do. The way that polynomial division works is that you focus mainly on the biggest powers of this. And you can write it in long division form, like you may never have done in primary school. I didn't do it in primary school, and I had to learn polynomial long division from scratch. So you've got your x squared. Technically there's a 0x as well. You've got your x to the 4 plus 0x cubed plus 0x squared plus 5x minus 1. Okay? For me, it's important to put all those zeros in, because what you want to do is line up all your powers of x. Okay, and the process works like this. It's two main steps. First, I take the biggest power here, and I divide it by the biggest power there, and I see what I get. So x to the 4 divided by x squared leaves me with x squared. Okay, now lots of people put this x squared over here with this x squared, but that confuses me. I need to remember for myself that this x squared came from that x to the 4, so that's why I put it there. If you prefer to put it over here to line up with that x squared, feel free, but I can't do it. Okay, x to the 4 divided by x squared is equal to x squared. And then what I do is I get this thing that I just got from dividing, and I times it by all of this. So x squared times x squared is x to the 4. X squared times 0x is 0x to the 3. X squared times 1 is x squared. So that's step 2. First I did this divided by this and got this, and then I go this times all of this and I get this. And then I subtract all of that. So x to the 4 minus x to the 4 is 0, as it should be. X cubed, 0x cubed minus 0x cubed is 0. 0x cubed minus x cubed is x squared is minus x squared. 5x minus 0 is 0. Minus 1 minus 0 is 0. Some people only bring down one of those terms. I bring them all down, because then what I can do is I can imagine that all of this is gone and just start here and do a new polynomial division just from that bit there. So minus x squared divided by x squared is minus 1. Minus 1 times all of that is minus x squared minus 0x minus 1. And then I subtract all of that. Minus x squared minus minus x squared would be 0. 5x minus 0 would be 5x. Minus 1 minus minus 1 would be 0. And that's what I have left. And I would then say, well, 5x divided by x squared, that's no longer a polynomial. Okay, x squared doesn't go into 5x, because I get 5 on x. So I stop as soon as the power here is less than the power there. So what I get is x to the 4 plus 5x minus 1 over x squared plus 1 is x squared minus 1. That's the final answer we got up here. Plus 5x x plus x squared plus 1. Yay! What I've managed to do is rewrite this rational function as a polynomial plus a rational function. And it means a whole lot of things about how I could imagine this function. I know that if x is really, really big, this bit will be 0 because the power on the bottom is bigger than the other one. So x to the 4 plus 5x minus 1 divided by x squared plus 1. If x is really huge, it's quite close to the same answer as x squared minus 1. So that function will be quite close to a parabola if I zoom out far enough. It'll just have a few awful bits, possibly, depending on whether the bottom can be 0, which it can't. Okay, all right. And I warn you, if you're going to do Maths 1A, this will come back in Maths 1A in about week 11. So just warning you so that you'll need to know how to do that, because in order to integrate this function, I can integrate that bit, and I could use substitution to integrate that bit. Whereas integrating this is awful. So one of the purposes of doing polynomial division is to turn a function into something that's easier to do its derivatives and integrals for. Okay, I'm just going to do one more, but with a linear function, because that's a little easier. Or maybe I should arrange one. Give me a second. All right, that's my final version. X cubed minus 2x squared minus x plus 2. Yes, okay. So I could do this polynomial division. So x minus 1, x cubed minus 2x squared minus x plus 2. So x cubed divided by x is x squared. X squared times this is x squared x cubed minus x squared, and I subtract that off. And what I'm left with, x squared cubed minus x cubed is 0, minus 2x squared minus minus, so plus x squared is still minus x squared, and I bring all the other stuff down. Minus x squared divided by x is minus x. Minus x times this is minus x squared plus x, and I subtract that. So this minus this is 0, minus x is minus 2x. And minus 2x divided by x is minus 2, and minus 2 times this is minus 2x plus 2, and they cancel each other out. And so I end up with x cubed minus 2x squared minus x plus 2 divided by x take 1 is x squared minus x minus 2. Yep. Plus 0 over x minus 1. So there's no remainder, I just leave it like that. So what I've finally managed to do is I've managed to factorize this. That's one of the main reasons that you are taught polynomial division, because that means if someone tells you one of the zeros of your function, the remainder theorem says that if 1 is a 0, then the remainder will come out as 0. So that tells me that if I sub 1 into this formula, it will come out to 0. If I had done x minus 2, the remainder would have come out to whatever you get when you put 2 into that formula. And what this means is that I can now factorize this fully, because I can use whatever process I normally use to factorize quadratics, which would normally be to just guess. So I need something that multiplies to give minus 2 and adds to give minus 1. So minus 2 and plus 1 should do the trick. And so I get these 3 zeros. Okay? So if you know some zeros, or you've guessed some zeros, then you can usually use polynomial division to figure out what the other ones are. So the normal thing that would have happened in maybe not an exam, but possibly an assignment, is you would have looked at this 2 and said, well, all my zeros, when I expand it all out, they'd multiply together to give that number, so I will try subbing in 1 and 2, 1 and minus 1 and 2 and minus 2, and see what I get. And when I sub in 1, it comes out to 0, so I won't even try finding the others because it's a cubic. I subbed in 1, came out to 0. That means I can divide by x minus 1 to figure out what the other bit is, and then I can just factorize it as normal to figure out what the other 2 are. So That's the procedure. Right, and I think that's pretty much everything in polynomials. It's good, 'cause it's about 10 minutes, or as long as you want to talk, to go. Do you have any questions about polynomials before I have any questions about anything in the course? I should point out that you can do polynomial division with complex number coefficients too. It's just much, much harder because you have to usually divide by complex numbers, which is hard. Yep?
Yeah, a question about the complex polynomials. It says in the 2011 exam, the question was find a 2-degree complex polynomial which has Z1 and Z2 as its two zeros, and write it in expanded form Z squared plus A1 Z plus A0.
Yep. Can I take it and I'll write it down?
Question C.
Okay. So this is 2011, is it? Oh, that would be 20,011. Algebra 6, C. Okay, so you're told that Z1 is 3i and Z2 is root 2 cis 3 pi and 4. Yep. And in part A, you converted that to 3 plus 3i, apparently. Okay.
Sorry, could you project that onto that one as well?
No. Like that?
Yep.
Cool. 3 plus 3i. That was part A. That you converted that, which if you want to know how to do that, probably complex numbers is a good place to look. And then part C, it says find degree 2 complex monic polynomial with Z1 and Z2 as its zeros. Yep? Okay. So degree 2 means it has an x squared. Monic means that the coefficient of the biggest power is 1. I didn't say that back there, but that's what it means. So just let me... Just going to add that to my notes back there. Yep?
Z2, wouldn't it be negative 3 plus 3i? Because the quadrant it's in?
Probably. I was just going on this dude's working. Yes, you're right. Because it's over here. Yeah, 3 pi and 4 is over here. You're right. I'm just going to fix that for you, mate. When you do your complex numbers, always a good plan to draw it so you can make sure you got your pluses and minuses right. Okay, thank you for letting me know that. Okay, so, well, it has Z1 and Z2 as its zeros, so that means that I can factorize it with sort of Z minus those numbers. So that means that my polynomial is Z1, no, Z minus Z1, Z minus Z2, or possibly X, it really doesn't matter, but they told me to use Z. Okay, so when you factorize a polynomial, it tells you the zeros. And being monic means that I'm allowed to just put Z there when I expand it out. I'll just get 1Z squared at the front. So I should be able to expand this out. So Z1 was 3i. Z2 was minus 3 plus 3i. And I should just expand it out. So z squared plus 3z minus 3iz minus 3iz minus 9i minus 3i times whatever 3i. Just expanding it out. So I've got z squared plus 3z minus 6iz, that's this bit and this bit, minus 9i. Now 3i times 3i would be minus 9. Okay, so I've got z squared plus 3 minus 6i times z plus minus 9i minus 9. I should probably write that in standard form and put the I bit second. And that's it. That's all there is to it. So in their thing they had it as A1Z plus A0. So in the exam that would be A1 and that would be A0 because they're the complex numbers. So I've rewritten it as z squared plus something z plus something, but those somethings are complex numbers. Okay, do you want me to do the next one? So part D, good, still recording. Part D says find degree for real polynomial with z1 and z2 as two of its zeros. Okay. Oh, it says monic as well, but that's okay. Right, so this time all the coefficients have to be real. So if something is a real polynomial, the only way to get complex zeros is to have complex conjugate pairs of zeros. So basically, since it's a real polynomial, the complex zeros come in conjugate pairs. Okay, that's really important, and it's something that we should go way back, and it's probably good enough to be a theorem. And it's just an important fact to know that if it's a real polynomial and it has any complex zeros, they must come in complex conjugate pairs, which means that so z1 equals 3i is a zero. That must mean that its conjugate is also a zero. And z2, which was minus 3 plus 3i, was it? That must mean that its conjugate would have to be a zero as well. Right. I'm sure I could use part C, but I'm just going to do it raw. So that means that my polynomial must be z minus 3i, z plus 3i, z minus 3 plus 3i, crap, and z minus 3 minus 3i. So what I've done is I've just taken all four of the zeros I have so far and put them in as the linear factors. Because it's a degree 4 polynomial, it has 4 linear factors, and I should be able to expand this out. So I'll do the complex conjugate pairs separately. So this is the difference of two squares. Z, well, it will be when I expand it out. So I'll get sort of z squared minus plus 3iz minus 3iz minus 9i squared, which is plus 9, so that'll be z squared plus 9. That bit there. And this bit, when I expand it out, z times z is z squared. Oh, I hate doing this. Just let me write it without the minuses, or I'll get it wrong. Okay, that's just better. If I don't expand the minuses out first, I'll just lose some. So if I'm really clever, I can think of that as the difference of 2 squares too. So I can have z plus 3 squared, which would be z squared plus 6z plus 9, minus 3i squared, which would be minus 9, so I get that. And then I'm supposed to expand that out again. Oh crap, I should have done them all with x's, because it said x in the notes, so I'll put the x's in at the end. So z to the 4 plus 6z cubed plus 18z squared plus 9z squared plus 9 times 6 would be 54z plus 9 times 18, 162. And so I did that because 18 is like 9 times 2, so 9 times 18 will be 9 times 9 times 2, and 9 times 9 is 81, so it's 162. Anyway, I just thought you should know how I did it rather than just, how did you do that? Z to the 4, just a second, plus 6z cubed plus 27z squared plus 54z plus 162. And technically they're supposed to be x's. So technically in z, my polynomial is that. So my final answer is, so in x, the polynomial is x to the 4 plus 6x cubed plus 27x squared plus 54x plus 162. Because in the notes, in the exam, it actually had x in that spot, so technically I should write it with x's because that's what it said. I don't know why they keep using z, but I think it's because z is x plus yi, and that sort of confuses people if you use x's. So there's two key points there. One is regardless of whether it's a polynomial, complex or otherwise, if you've got the zeros, then it's just x minus blah times x minus blah times x minus blah, however many you've got. But if you know it's real, then all the complex ones have to come in conjugate pairs. All right. Anything else about polynomials? Cool.